Okay, let's go ahead and pull ourselves back together. So getting started on the second side, people have been asking over the break about assignment 4, which is being, we sort of drafted it all up this morning. Lottie's going to be transcribing that and getting that out hopefully later today or tomorrow. It's going to be basically due next Tuesday. It's basically going to be a lot of what we've been doing here, just taking a basic building program, making a conceptual mass out of it, doing the energy analysis on it, and ultimately converting it into these sorts of building elements. At the end of the assignment, you pretty much want to have a skin of a building. Okay, that's what you're asked to. Okay, and what we will be doing then for assignment 5, the following one, which will actually take us into the Thanksgiving break and into the final week of classes, okay, is actually going through and within that building skin, starting to add structural elements and some mechanical parts to it and some plumbing parts to the building. So you actually start thinking about all the different systems and how they work together to fit within the constrained space we have available. So you can really think about designing all aspects of the building and getting them to work together. Okay, for the final one, that'll actually be more of a group assignment where different people will be able to take on a role you want. So if you like to think of yourself as a structural engineer, or if you have an interest in doing some mechanical design or some plumbing design, you can take on a specific role to design a part of the building, and then ultimately we'll have you coordinate your work so that we find any sort of conflicts or any sort of issues that arise from people working independently, which actually sort of mirrors the real work process. It's exactly what's going on in so many design projects right now, is that people are working on all these different aspects of the building as independent designers. Things come together in the finished building, but we have to coordinate that work and really make sure there aren't any overlaps and interferences or conflicts, because we're all fighting over sort of a very limited amount of space. So let's use that as a motivation just in terms of thinking about the next part of what we want to get started with today. And what I will do is actually just open up something, a different file, which is currently hanging around out there on coursework. So under session 15, it's 15 already, it's hard to believe for me that it's already like session 15. But under session 15, I'm going to open up something called the architectural model, and we're going to look at a building from several different aspects, just thinking about how they could start working together. This is a little building design I did for class a couple of years ago, which is really around about the notion of creating a small building and how the different systems could work together. So the idea with this building is, it's actually very similar to a lot of buildings that we build around here. There'll be some retail space down on the lower floors, some office space on the upper floors. Office space, which is, it's kind of defined as office space. We don't really know who the tenants are going to be or how we're going to divide that space up just yet, but there's some just office space of that upper floor. And within those upper floors, let me see if I can kind of come up with a nice section of the building to kind of show you how this works. We have some lower floor space that's a little bit, very, very open. Going to be more retail space, some office space up a little bit higher around some central corridors. There'd be like a shared conference room on each floor. Like some sort of atrium that lets some light come in from the top of the building all the way on down. But even within this building, there'd be some shared facilities. So if I get up to level 2, for example, you see the idea is that on the individual floor, there's some notion of a shared stairway, some elevators, and some bathrooms, men's and women's bathrooms, as well as a little bit of mechanical space. It's just, it's not perfect, but it's enough to kind of get us going, thinking about how the different spaces of a building work together. And it's very common to sort of go through and design buildings in this way, thinking about the skin and the spaces we want to create together, any sorts of shared facilities. And often we have a core to the building, a core which really starts to bring up the elevators, the stairways, things that sort of, the mechanical equipment, the plumbing, like all those things being very concentrated in one very focused area. Because having all that stuff focused in that concentrated area just brings you a real efficiency. So it's often very common to kind of bring those things kind of very close to each other. Now, just relative to kind of thinking about the class and what we talked about last time, I realized that this building would probably actually need to have 2 stairways as opposed to a single one. It really depends on this issue of how far the exit path is from any office to getting to the evacuation route. If the building was done this way, I'd probably need to have some fire escapes or something like that on the ends. because the idea is really for egress, you do like to always have two exit paths so that if, for example, if I was down here in the building and there was a fire somewhere over here and it was blocking my way to the staircase, I'd have another way to get out. So more common would be a staircase at each end. And you can almost see that in a lot of the buildings we work with here on campus. For example, in Y2E2, there's staircases in the center, like in the blue atrium. There's one in the red atrium. There's one in the green atrium. They're often kind of at the ends of the building because it gives us these different evacuation paths. So no matter where you are at any one time, there should always be two paths, even here. Notice in the room, there's a path over here, there's a path over there, because if there was a fire on this side or we were blocked on that side, you still need another way to get out. You don't want people to be trapped. Okay, so egress is a very big thing as we're thinking about building design. So this basic little building design all started with the notion of an architectural space, but inside of this architectural space, and to support this architectural space, we need to actually start thinking about how the structure is going to work, how the mechanical systems are going to work, just how it's all going to fit together. If I switch back over to that 3D section view, you'll see that in my architectural planning, I've actually done a little bit of accommodation for that. I do have incorporated in here some sort of notion that there's, some sort of a ceiling system underneath the floor system. And there's a little bit of space for us to work with. But let's think about the complexity of what actually has to happen in that space. So in this space, the space that's typically above the ceiling there, if the beams aren't exposed, and that's going to be a decision we can make about whether the beams will be exposed and we can see them or we want them concealed. Okay, we basically have to include structural beams, okay, anything that's going to be necessary to support the structural loads. Okay, we often typically have to go ahead and include some sort of mechanical ductwork. So any sort of air handling typically has to be through that same space, as well as sprinklers, these sort of fire sprinklers, as well as electrical. There's a lot of stuff that actually hangs around up in that ceiling space. So let's just kind of think about that. Like in this room, you can't even sort of see the structural space because it's all hidden from us right now. But there's structural. Okay, there's mechanical, and I'll use the word mechanical to mostly mean HVAC, or heating, ventilating, and cooling. Air conditioning in there. Okay. And even in this space, you can't see them, but you can hear the fans. Actually, you can sort of see them over there. There's an air intake right above you, right over there. There's an air intake right above you over there. I'm trying to think what the fans are blown out. So I can certainly hear them, or that's just the conductor sound. Okay, but it turns out ductwork actually takes up a significant amount of space. We also have a couple different types of plumbing systems. Plumbing actually has a lot of different variations to it. There are what I'll call water supply systems. So that's the hot and cold water that actually runs to the faucets and the toilets and things like that. Just things that are actually providing water. We have the whole sanitary system, which is really, if we have waste that we want to evacuate and kind of get away from the space, how we go through and do that. We also have sprinklers. So fire sprinklers. And you can see them, they're hanging around in here, trying to look very innocuous. There's one right here, there's one right here, there's one over there. They're determined by, there's a pattern of really how closely they need to be spaced based on the amount of water pressure, and if they're flowing water, making sure that we get really good coverage, that everything ultimately gets doused. Okay, and they're really a lot more common than you think. They're all over the place, hopefully looking relatively innocuous. Now, plumbing systems have even got a little more complicated lately because we not only just sort of have water supply and sanitary, what sort of happened recently, as we started thinking more sustainably, is we have gray water systems. Okay, where we actually try to take some of the water that is, well, we'll split the sanitary. We have the waste, which we aren't going to go ahead and recycle from the toilets, okay, and send that water off. Okay, that's called black water. But we have waste from, for example, the sinks, okay, where it's just the soap from washing your hands. Those tend to go into something called gray water, which can be recycled. So what ends up happening is gray water often gets captured and then fed back into the system. But it gets fed back in sort of a very specific way. Okay, well, we take that gray water and we're going to reuse the water. When you see in the restrooms here that it all says that this is, reusable water, okay, they're basically telling you don't drink it, okay, because that's water that has had some other use. Gray water is great for flushing toilets and things like that where you need the water to go ahead and kind of create the motion, but not potable water. Okay, so we'll distinguish those from potable water. And we have a whole other variation on this, which is the water that we captured from the rain, where we on the roof ultimately have rainwater and capture systems, and we try to kind of collect it in cisterns that we can reuse later. So plumbing's actually gotten sort of incredibly complicated in terms of what's going on.
Question?
Yes?
The water coming out of the sinks, that's always fresh.
That's clean, yes.
Okay. So they're saying don't drink the water out of the toilet?
Yes.
Just checking. Because I fill up my water bottle.
Oh, no, exactly. No, that's actually fine. That's right. The sink it's potable water, the water fountains are potable water. Yes, but it sounds strange that we'd have to tell you not to drink the toilet water, but yes, that's what it means. Okay, and finally we have the electrical systems. And electrical systems, there's a whole bunch. There's sort of the power, but we have all the alarms and controls and AV and networking, and there's really all these different systems. High power, low power, there's a lot of systems that go into a building and how they're all kind of working together. So buildings are really kind of incredibly complex organisms. And as you think about trying to layer all these things in, let's kind of think about that there actually is a hierarchy in a way you approach this. Okay, in the scheme, often different people will design each of these different aspects of the building or even sub-aspects. The people who are designing fire sprinklers, very specialized discipline, quite different from the people who design most of the water supply systems, okay, especially if we're doing sort of a more sustainable system. On the electrical side, the power people are very different than the alarms and the control people. Okay, and there's a lot of people whose work we have to keep coordinated. But as you think about this, okay, I've got an architectural design over here. I got some space allocated for all that stuff to fit into. Okay, how do you think we might start? Who do we turn them all loose and say, hey, go ahead and knock yourself out. We got space available. Everyone come up with an independent design, and we'll try and figure it all out later. Or how do we get started with something like this? So how would if you had this task, if you were a designer, where would you start? Who would you start talking to first? Yes.
Structural.
Yes, I think structural is a great place to start. Okay, if we start thinking about all these different functions, there's kind of, what I'll say, it's kind of what I'll call the downstream impact of everyone's decisions. And you always want to go through and do this in a way that the people who sort of have the most downstream impact on other folks really get their design decisions made first. Okay, it wouldn't make a lot of sense to go ahead and, for example, put all the plumbing systems in place, and then later on when we figured out that we had a conflict with a structural system, to say that, the structural engineer needs to move all the beams. Part of it's downstream impact, part of it's this whole notion of ease of relocation. So if you and I are going to be fighting for space, basically it's not just who's the biggest bully, there really is some notion of, your stuff may be easier to move than my stuff. So I'm going to have you move yours, or my stuff may be easier, and even though it's going to be inconvenient for me, there tends to be sort of a hierarchy to this about how we work. So structural, almost invariably, they get number one. Because really, making sure the building stands up structurally and that's all handled right, that's a primary concern. You have to take care of that right. They often are first in line in terms of making sure that things are going well. After that, all the systems have to work right, but it gets a little bit fussier or a little bit more contentious about really who should dominate. If you think about each of these different sorts of systems, the mechanical system with all the ductwork, the plumbing system, and the electrical system, Do you have any sense about which of those is going to be easier to move? Like, what's the hardest to move? If you're thinking, I know it's kind of hard, you haven't actually had to design some of these systems, but here we have metal ducts and all the elbows and connections to kind of make them fit. Here we have pipes, and here we have like electrical wires and conduits. And you think about those, which one feels like the hardest one to move?
Mechanical.
Yeah. Of all the different things, mechanical design tends to be, relatively harder. It's got these big old ducts. They're 12 by 18 or round, these big old kind of mechanical sections. They're kind of finely tuned to deliver just the right air to all the different spaces. Yeah. Actually, having that designed optimized, having that system perform well is probably tougher than the other ones. So they often get in, I think, with a second priority, although this will vary. On every project, every project manager gets the option of really determining whose concerns get to dominate when conflicts are found. But mechanical is probably a good number 2. Next up, we have the plumbing and the electrical people. Some people, like of all these different systems, like water supply, sanitary, and sprinklers, for any of those, like which one sounds like that might be the most complex or the hardest to relocate? And if you think about the physics of the system, it'll give you a clue. Like of water supply, sanitary, and sprinklers, which one of those sounds like it's actually the hardest in terms of the physics? Yeah, you're actually right. Sanitary is actually the hardest right here. Let's talk about why that is. Okay, with sanitary, you basically have the stuff that human waste likes to flow downhill. Okay, that's something I learned back in high school. It's like this whole notion that when you're doing the plumbing that waste flows downhill. It is not going to go uphill no matter what you do. It ain't going uphill. So sanitary systems are designed that have a little bit of slope to them. So from the point of the fixture, from the point of that toilet, from the point of the urinal, like that water it's going downhill. It's not going to go uphill no matter, unless you put a pump in there or something like that to kind of do that. So that actually sort of dominates that. Water supply that has pressure behind it, like the hot and cold water, even the sprinkler system, that will go uphill. You put enough pressure behind, it'll go up and kind of get into the ceiling space, work around other things. So what tends to happen is for these other systems here, they're subordinate to sanitary. So, or whether sprinklers or water supply comes first, don't really know. Either one of those could be number 4. They're typically designed by 2 different systems. Sprinklers tend to be sort of a more constrained thing in that the fact that I actually have to have these sprinklers at a very regular pattern, that sort of dictates some specific things about how much piping and how much loss I can have with all the different connections. They're somewhat tight. Water supply is really, really easy. You can bend it around, go anywhere you need to. So that's pretty easy. Finally, electrical. The poor electricians, they really lose out in this, only from the standpoint of trying to just have the space they need. People look at ductwork or conduit and Romex and different types of electrical cable, and it's really easy to bend that to be there's no huge bending requirements. It's just pretty easy to put in wherever you need it. So somehow they're often the last one to be kind of considered, or they're considered to be the easiest to move. So we got a lot of stuff we need to go ahead and put into that small space. And today, we want to talk a little about the structural side and the mechanical side and how we work with those 2 things. We'll continue with thinking about plumbing and electrical. So, I got my basic space over here. It's like basically my architectural space. What I want to do is actually start thinking about putting a structure within here. And to do that, I'm actually going to open up another project, which is actually out there on the coursework server. It's called Structural Model Grids Only. Actually, let me open the other one. Show you where we're going. This is actually a structural model of a structure for this building. So within this, you can see columns and beam systems and floor slabs and all the different things that are ultimately going to be a part of the building. But we're going to get to this, and we're going to sort of build this up like one layer at a time. We started playing around with this a little bit, kind of a couple sessions ago and thinking about a structure. But we'll kind of do it with a little bit more care this time in terms of thinking about how we got to this structure. The important thing to sort of know about this structure is whether it's steel or concrete, and this is illustrated in steel right now. I could just as easily kind of do this in concrete. The same basic principles apply. It's really just all about the types of materials and what the connections are. And every type of building construction has its own funny little nuances and disciplines to it. Concrete, it turns out, is actually, from a modeling standpoint, a little bit easier to work with. It's not necessarily easier to construct. It may be much more common in your area, used very commonly as a building material because it's local and it's very easy to access there, whereas steel tends to be very more precise but also more expensive. There's sort of a variation in there. But in terms of modeling things, concrete tends to be fairly forgiving because with concrete, as we model it, very often if we have a beam and another beam coming together, we just sort of say those concrete beams are coming together, where with steel, we have to actually be very precise about how those things happen. They don't just merge automatically. So let me switch on over to, this one that said, let me kind of close these other views. I'm going to say, let's do the grids only version. And this is actually a series of structural grids that's been designed to fit within that building model. So you'll see there's a number of different grids, 1, 2, 3, 4 in one direction, A, B, C, D, kind of going all the way through H in the other direction. But it's really just a series of structural grids. And really, how did we come up with these structural grids? These are just what we thought sort of good structural locations would be relative to that building model. So if you want to sort of see that building model relative to this, I can go through and I will link the building model to this. Oh, it's open in another document, so it doesn't want me to do them both at the same time. Let me close the architectural model. And I will link it to this. We'll talk more about linking next time. I'm just doing this more to give you context right now. But, hang on. When I'm linking models, we'll learn all about, when we're linking them, not to choose the default assumption, which is centered by center. But I'll say origin to origin. We'll actually link them up like this. But you can see, relative to the architectural model, I've just laid out a pattern of where I thought good column locations would be relative to the architecture. Okay, so those are just different grid locations. But where are we going to get going with all this? We're going to go through and start by just placing columns at all those grid locations and beams at all those grid locations, and ultimately something called a beam system, which are joists or some smaller type of beam that'll span between these. So the idea is I want to get columns at each of these locations, each of the intersections. I want to put beams along the major lines, and then filling in the major lines, I want to put a smaller system. You call them either joists or web joists, or just something that if this is 30 feet across, the floor slab itself probably can't accommodate that. We need to put some sort of subordinate beams, some smaller beams in there that'll bear on the bigger beams. And that's really where we're going with this. Okay, it's just sort of putting all this stuff together. So let's go ahead and take a look at that and how we do that. Now I have this linked model turned on right now. What I'm going to do is actually just turn that linked model off so you can't see it right now. Just because, it'll sort of clutter up our view and make it just a little bit harder to see. So under manage, I can say manage the links. Let me just unload that for right now. So we're back to just the grids only. So when we want to start modeling structure stuff, it all starts with just choosing the structural tab. And we have beams, columns, beam systems in here. These are the big elements we tend to work with. There's this notion of basically just choosing different elements, for example, the wide flange column, and placing them at those grid locations. Now the types of columns that are available to us, I have some rectangular columns here, I have some wide flange columns here. That's just determined by what's loaded into the project. So if I want to put concrete in, like round columns versus concrete rectangular columns, what I can do is just say, let's load a family and bring in a different one. So for example, I'll go out to structural columns, concrete. Let me get the concrete round column. Square columns we have there. These are ones you might be familiar with, dropped caps. If you have a flat rectangular or flat concrete slab, often we have something that looks like that, a flat cap to prevent shear punching at the column location, or kind of something that's a little bit lesser, kind of like a little low pyramid capital on it. I'm just going to go for the round columns now. But if I want to go through and start placing some columns, here's how you do it. Let's just work with those round columns for now. I'm going to go through and say columns. We can go through and place them individually, but I'm going to actually choose at the column grids and just choose. Oops, actually I am bad. Let me go through and say columns. Let me take a look at this one. This is that whole issue of depth versus height. This is that funny thing. If I get structural engineers and architects into the same room and we talk about what should show on level 1, we'll get two different opinions. The architects will say you should show the columns that go from level 1 to level 2. The structural engineers will tend to think that it's level 1 down. See? So, depending on whether you like to think down or up, either way, doesn't really matter as long as we get them in the right place.
So height means up and depth means down.
Yes, correct. So height would be going up to level 2. Depth would be going down either a set distance. In this case, I don't have anything below level 1, so I don't have that option. So let's go height to level 2. Apologizing to all my structural engineering friends in the crowd. Let's choose the grid option, and I'll just go grabbing some grids. So I'm just happily going around, I'm control clicking to grab these other grids. Okay, and by doing that, theoretically, I think I'm going to have 32 columns. Let me see if that works when I say finish. Okay, I'm popping it up. That's just a little bit section boxed off right now, so you can't see it. There we go. So hopefully I got 32 grids in there, or 32 columns in there. Now again, those are concrete columns right now because that's what I chose. If I wanted those to be steel columns instead, there is no problem at all. They are just different types of elements in Revit. So I can choose all those guys. Oh, I know what it is. That's interesting. I have the analytical model turned on. Let me tell you about this. There's actually two different models going on here. Within Revit, as you work and you place structural elements, there are the columns themselves, the ones that you think of as being the physical elements. There's also something called an analytical column. That is the single line representation of the column that is used for analysis. So let me turn that off so I'm not selecting those. Okay, now I can choose if I want those to instead be some wide flange columns. I could choose to those. So depending upon whether I want wide flange columns, whether I want round columns or rectangular columns, whatever it is, I'm just choosing different column types. And whatever system sort of makes sense to me. So you're placing them the same. It's really just sort of an issue of what column type you're choosing. Let me turn off that section box. That's going to bother me in just a minute here. Okay, next up we're going to put some beams in here. In terms of the beams, let me zoom on out here. We can again go ahead and place them in a number of different ways. I'm going to come back over to, the level 1 plan again. Actually, I'm going to put them up on level 2. They'll be easier for me to see on level 2 because at level 2 I'm looking down and these are really at the top of level 1. So if I choose them at level 1 and I'm putting them over my head, I won't see them. So I'm going to go to level 2. I'm going to put some beams in here. So I'll choose the beam element. I can choose, again, some sort of steel element, some sort of concrete element, whatever we have in mind. Now notice, this is where it's going to start getting interesting. These concrete beams are 16 by 32. Okay, that's pretty tall and 16 wide by 32 deep. That might be consuming an awful lot of that space. So I do have an incentive to actually think about something a little bit smaller. Now, 12 by 24 may or may not be big enough. Okay, I might have to go ahead and upsize those a little bit later, but this is where it's going to start being an interesting tension between my architectural need and my structural need and trying to figure out the right balance between those things. But one thing about concrete as a system, it's very easy to model, but at the same time, it's pretty hard to violate. Like, it's hard to stick a piece of ductwork or piping through a piece of concrete. Okay, you can do it, but it involves some work. So let me try putting those in there as some 12 by 24 beams. I can say on grids, and I can choose this grid. I'm just choosing grids galore. Let me finish that up. Take a look at that in 3D. And not too awfully bad. Just so you get a sense of what's going on here. Oh, you can see those concrete columns and those concrete beams. This part right here, you see that little orange line? That's the analytical model. That's what's considered to be where the loads would be applied. Or if we had to reduce that beam into a single line representation, that's where it would be considered to be applied. Okay, but we're going to ignore that right now. That will become more important when we start doing the analysis. So I got those beams, but they're still looking pretty tall in terms of the scheme of things. We might need to go through and change those a little bit later. Okay. If I was going to go through and do this with steel as opposed to with concrete, here's one of the few differences in terms of working with concrete versus steel when you're doing the modeling. As concrete, okay, if you're going to have to put the beam in here, and you're going to put a concrete slab on top, the concrete beam can actually be right up to the top of the concrete slab. They'll just sort of merge themselves together into some nice, like a magical structure where it all... Yes, so the slab is actually considered to be part of the depth of the beam. Steel, you don't kind of get that luxury. So for steel, if, for example, I was going to do this as a steel beam, or all the beams as steel beams, let me go ahead and pop it over and make it a steel beam instead. Okay. Steel doesn't get to ride up at the top. It doesn't merge automatically with the concrete slab. So steel we always have to reduce so that it's below the slab. It's supporting the slab, but it's not actually merged into it. So what do you need to do? You can choose your steel, but we have to put in something called a Z offset. That's just going to drop it down in the Z direction. So if you're going to have steel beams in here, the only difference you're going to have, really, one of the high-level differences is I'm going to put some sort of offset to drop that steel beam down. Now, how big is that offset? It really just depends on how thick your slab is. Okay, so if you have a 5-inch slab, drop it 5 inches. If you have an 8-inch slab, drop it 8 inches. Whatever it is, you just want them to ride underneath the concrete as opposed to be merged up into it. Okay. So that's like one of the few differences you have to sort of start playing around with, just thinking about steel versus concrete. Steel tends to be nice in that steel members are somewhat easier to poke holes in and kind of have open web systems. But, yeah, we'll go ahead and get started this way. Now, you're looking at this and you're thinking, okay, I'm all set to put a slab across this. This distance of 30 by 30 might be a little bit big though, so let's kind of talk about that. Very often, this spacing, I'll make that back to concrete, it's going to bother me here in a second. Be consistent. There we go. Okay, this spacing may be a little bit large for what the slab can actually span. If it was steel, I'd say definitely it's large. Concrete kind of depends on how we're designing it. But if we need to subdivide these bays into smaller systems, so we have the major beams and we have some secondary beams which are actually going to support the slab and carry loads back to the major beams, we can do that too. And that's something called a beam system. Beam systems are really just beams that are sort of set up on a very regular pattern. So a regular spacing, just sort of a very regular pattern you want to apply them to. So things like joists, floor joists are a beam system, rafters are a beam system. It's just a series of structural elements that's going to have a very repetitive pattern to it. So if I choose the beam system, at some level it looks amazingly similar to the other choices. We have this whole notion of, oh, really, what is going to be the type of member that's in that system? You know, whether it's a concrete, something or other, or a steel beam. Let me put some little steel beams in here.
Are the main beams called girders?
Yes, often you'll call them girders. The beams that collect loads from other beams tend to be called girders. We could sort of put some sort of fixed distance in here. Let me make them every 6 feet now or something like that. I can choose to basically pick supports. I can draw lines, or what I tend to actually like to do is actually choose like beams that they'll rest on. Actually, I see I already made a little mistake in there. In terms of right now, the work plane set to level 1. The work plane being set to level 1 says that as I place them, the beams are going to show up on level 1. So what I actually need to do is change that, set the work plane to level 2 instead, because I want these little secondary beams to be at level 2 also. So I can actually choose this little set the work plane and reset that to level 2. Okay. Now when I draw them, they'll be at level 2 as opposed to being at level 1. So I can choose these different beams around the outside, and the only important thing you have to worry about here is the first beam you select will determine the directionality of the system. Okay, so the beams that you put in the subsystem will always be running parallel to the first thing you select. You can always change it later. But if I want them to go this way, I'll choose this or that. If I want them to go this way, I'll choose that or this. So, for example, if I choose this one, and close that on up, get a little secondary beam system in there. Now the cool thing about beam systems is they actually have their own parameters, so if later on you decide that it needs to be 5 feet or 4 feet, whatever it is, yeah, they change really quickly. They operate as just a repeated series of elements. Yeah?
What if you wanted to go 4 feet
From the edge? Ah, a very good question. Okay, let's get the beam system. See if I can grab it. Okay, it actually has this notion of the justification. Is it justified so there's a whole increment at the beginning? Is there a whole increment at the end? You know, or is it just centered? So, yeah, it'll take that 4 feet, and you get to decide, like, you know, what will be honored and where the leftovers will go. So centered says make it 4 feet in the center and just break the difference on the edges. Okay, but if you really want them to kind of be coming in a single direction, can't really see much different here. Let's change it to something much broader that'll be a little bit easier to see. Let's say that it was an 8-foot distance. Okay, so now I can decide whether I want that to be centering the distance, putting it at the other end, just really how I'd like to break that up. Yes, Sarah, what you got?
Do you want to edit the dimensions or type of the framing system? You
Mhm.
just go to edit type and then you can make what you choose the material and stuff like that.
Cool. So for the system, if you choose the system, there's this option here about choosing the type that's in the system. Okay, so you can choose it there, and if what you have isn't there, you know, or if the size you want isn't there, no worries. For example, all we have right now are the, what is it, like these 12 by 24s. That feels a little bit big. If I wanted to have some like 9 by 12s or something like that, I could choose the beams. Let me, what do I got in there? Nothing nearly that small. Let me edit the types, duplicate it. I'll say I'm going to have some 9 by 12s. Then the base will be 9 inches. And it'll be 1'0" tall. Okay, so now I have a new type available. Then I can choose this system and make those 9 by 12s instead. Now, Revit's actually pretty smart, especially with the concrete, on this whole notion of the rebar cover. You know, it'll ultimately help you place rebar according to the spacing and the clearances that need to sort of happen within that beam. So it gets to be pretty good about that. Now, as you're going through and creating these things, beam systems, let me see if I can find the other mode. Does it even work in here, in that direction? Maybe not there. Let me do it on level 2. There's this sort of way of doing it automatically, which I sort of like because it's really quick that way. If I go to level 2 framing as opposed to doing it in 3D, I'm not seeing that. There's something where I can actually kind of create them automatically in terms of space. Well, not to worry. We'll just go ahead and create another bay over here. Finish that up, and I'll do another bay over here. Say again? You certainly can. That would be a most excellent idea. You got that whole system right there. Let's just copy it and paste it over to here. See if I can actually get it right. And copy it over here. And bring it across like that. Now, once you do this, imagine that I've completed some more of the beam system, because I haven't, but I will go ahead and imagine that, just out of the interest of time. We can go through and finally put in the floor. So I'll put in, I could do the concrete on the lightweight deck, or I could just do a 6-inch concrete slab. Again, I'm going to go through and just choose some supporting beams. I'm going to do this funny thing that I tend to do where I don't choose all the individual segments. I just choose like 4 lines to define it and do the trimming, just because I think that's a little bit stronger. Okay, even here, the floor slab has a directionality to it. We can decide whether we like that direction or change it. So now I got this nice floor slab throughout the whole thing. It's actually not looking too bad. I might need to poke some holes in there for my atrium and my elevators and things like that. But once I have this, I can then grab all these things and using my ever so popular, I love to do it, copy and paste to other levels. I'm going to take those beam systems, the floors, the structural framing, girders versus joist. So you see it actually sort of does that same thing in terms of thinking about using those labels. Copy it to the clipboard. I'm going to paste it aligned to other levels. This is the part that always confuses me. I know now, because I've done it enough times incorrectly, that I'm going to copy that up to level 3 and roof, because it considers those beams already to be on level 2, so I don't need to copy them to level 2. And justifying with the way the structural engineers think, it'll think of those columns as actually belonging to level 2 also. So with a little bit of copying and pasting, I got my basic little system here. Not too bad looking. There's a couple things I want to do to it just to kind of finish it out. Oh, under those columns, I'll probably need to put some sort of footing. So I can take a footing, and there's different sizes available. But I'll say let's just put them at the columns. I can put a footing under there, a footing under there. Oops, I have to control click to get a bunch. And hopefully you get a sense that it's pretty quick. That one's going to line out in space to go through and start creating a structure. So this part feels pretty good in terms of, hey, getting the basic structural skeleton. That's not too bad. And again, I could show you doing all that in concrete or in steel. The big difference is going to be just changing the column types and then just really worrying about that alignment, what the height is relative to the slab, just so we don't have any sort of steel conflicts within there. This part's looking good for the structural part, so structural engineers feeling pretty happy. The problem now is we have to go back and put some sort of mechanical system in there and find room for all the ductwork that we need to do. So let's go ahead, we'll pick that one up on Thursday when we get together in the morning. So on Thursday, we'll take a look at the mechanical systems and how we run both the HVAC as well as some of the plumbing and get all that stuff to sort of fit within the same very constrained space. And we'll see that, you know, we've got some challenges ahead of us to go ahead and do that. Not so much from the building modeling standpoint, but even just planning it out about how they could possibly physically fit. We got some design challenges ahead. Okay, so let's adjourn for today.